Hello. This video is about how to find the energy stored in a moving system. And we call this kinetic energy. When something's moving, there's energy stored in that moving object. See, how can we do this? Let's draw the ground. Here's the ground. And I'm trying to imagine a simple situation. So let's call this a frictionless surface. Something like ice would be very low friction. This is less than that. This is frictionless, okay? And let's just talk about a really complicated shape, like a block. And we'll imagine that you drag a block or a box across the ground. So this is you dragging a box across the ground using a rope, okay? But the first moment in time, time zero, none of this is moving, okay? In the end, you're moving fast, okay? There's your rope, okay? And this system is moving very fast. Now, it gets better. Between these moments in time, I want you to recall what you learned last semester, all right? I want you to pretend that between moment A and moment B, between the moments in time, we had constant acceleration, okay? And our system is going to be this box or this block, all right? So I'll make it mass M. I'll just call it a box system. And again, the system has mass M. It's moving with a velocity v after this time interval, okay? So that's the situation I'm envisioning that I think will help us figure out an equation for kinetic energy. Now within our box system, let's see if we've got any energy stored in the system. E.g., E.k., E elastic. All right, and I'll copy that over to the end as well. So our system in the beginning, our system in the end. Let's go through this. Is our system moving in the beginning? No. It's moving in the end though. Is our system changing height? No. So EG doesn't change. So since this is an equation, EG just simply cancels out of the equation, right? Are there any elastic molecules in this particular situation in our system? That just says box. It's not a spring, it's not a rubber band being stretched, it's not a trampoline. Elastic is irrelevant in this particular problem. So now what do? We got the energy stored in the beginning. We got the energy stored in the end. Well, wait. There's no energy stored in the beginning in our system. All of a sudden there's EK in the end. What happened? Is there a force on our system? Oh yeah. If our system is this mass, this rope pulled on the mass. So we could say that the rope did work on the box. And this W stands for work, right? So we're adding energy in the form of work during the time interval between these moments in time. All right? And we're going to ignore dissipating energy, ignore any dissipating energy out of our system. Cool. So we would subtract E dis in this equation, but I'm going to cross it out because we're going to ignore it. So we're going to pretend that there's no friction. We're going to pretend that there's no air resistance. We're going to pretend there's no energy leaving our box system. All right? So our equation becomes work is equal to kinetic energy, right? This means that the work that the rope does on the box is equal to the kinetic energy at the end. So the work done on the box during the time interval between moment A and moment B, the energy put into the box during this time interval has to equal the kinetic energy we've got in the end, okay? I should also make a note that my box was here in the beginning, and then I'm going to move my 0 right there. So my box moved this displacement from beginning to end. It moved this delta x here, okay? And this would be its final position. That would be its beginning position. So the change in position is located right there. Actually, change in position is a vector. So let me fix that. It's a vector from where you start to where you end. So it's a vector going this way to there. So that's my displacement vector. Okay? I'm just going to worry about the distance, though, because you should know already that in order to actually do this, in order to drag a box across a frictionless surface so that it accelerates, this rope would have to pull with a constant force. Okay, that's a little hard to imagine, but if the block is continuously speeding up, the person running has to run faster, 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 and that would keep the rope tight. If the person walked with constant velocity, it's not going to work. The rope's going to not stay tight. The rope's going to go slack. So what we're talking about then is a graph of the tension versus how far the box moves, and the tension in the rope has to stay constant. So the work done on the box is going to be the tension times how far the box moves, right? So let's go back. So I can plug in tension of the rope. All right, tension due to rope times how far the box moves, right? And that's got to equal to EK, all right? So now if I scroll down, well, let's talk about what tension in the rope has to equal, all right? So let's draw a force diagram for the block while it's accelerating, okay? Force diagram for block while it is accelerating. That's between moment in time A and B, okay? What's also going to be useful is if we can draw a velocity graph. For the block. Again, this is while it is accelerating. And we're assuming the acceleration, again, is constant. Accelerating. All right, let's start with a force diagram. We got weight. No, that's normal force. Tension, weight, normal force, and the rope is pulling to the right. Okay, there's no friction. Okay, so if we do the sum of the forces and we add the vectors, right? We got normal, we got tension, we got weight, right? Normal, weight, tension. Well, you should be able to see from my sum of the forces diagram, if I draw my resultant vector, this red vector is what I get from adding these. This red vector is the sum of the forces. Well, sum of the forces by Newton's second law is equal to ma, and you can see that tension has to be equal in magnitude. In other words, ma has to be the same length as my tension vector. So tension is equal to ma. I'm going to use that back in the previous slide. All right. Now I also want to draw a velocity graph and use a couple things from that. Okay. So if something is speeding up, then the velocity time graph looks like what? Let's assume the speeding up is the same each second. I hope you realize that it's going to look like this, right? Now, which part of this graph is your acceleration? That would be the slope, right? So the slope of a velocity time graph is our acceleration, which means acceleration is change in velocity divided by change in time. Acceleration is a vector. Now, in this case, we start from rest. That means zero velocity. And we speed up to velocity v in time t, okay? I just made up v and t as appropriate symbols. So since we start from rest, I could just write v over t is going to be my acceleration, okay? That's going to be the magnitude of my acceleration. So this doesn't identify direction because I don't need it for energy. So magnitude of acceleration is all I need here. I need the number. The other thing that this graph can help us find is the displacement, okay? The displacement should be the area under this graph. What is that? Isn't that going to be Vt, V times t?
Teachers, please excuse this interruption. Will the student by the name of Shelby Fowler please report to the attendance office? Shelby Fowler, report to the attendance office. Thank you.
Thank you. If we take Vt divided by 2, that's the area of this triangle, right? So let's use this. Let's use this. And let's use this back on the previous slide. So try to remember that how far the box goes is going to be Vt over 2. Let's remember that the acceleration is going to be V over t. And let's remember that the tension has to equal in magnitude to ma. All right? And this thing's going to wrap up real soon. Cool. So on the page I was just at, I showed you that the tension is going to be equal to the mass of the block times its acceleration. Okay? Now I'm going to leave the rest of the equation alone. Okay, sound good? Now let's focus on this part of the equation. Okay? On the previous slide, this was the area of that triangle, which was what? Velocity times time divided by 2. Okay? Now I'm going to rewrite the whole equation again. So I've got ma Vt over 2 equals Ek. Almost done. And if you recall, the acceleration was v over t, right? So the acceleration was v over t. Let's plug in v over t for acceleration. And here's the rest of our equation. Vt over 2 equals ek. Do you see what happens right off the bat? Our t's are gone because t divided by t is 1. And our equation simply becomes kinetic energy equals 1/2, that's the 2 in the denominator, m, that's the m, and there's 2 v's there, so it's going to be v squared. So let me write it correctly here. Kinetic energy is equal to 1/2 mv squared. Okay? So that's how you could derive an equation for an object moving, for the energy that's actually stored in the object while it's moving. Okay? Stored in the object's motion, we say. Sound good? Hope you liked it. And thanks for watching. Have a good day.